Well, thank you very much, Luis, and thank all the organizers for giving me the opportunity to speak here. I actually thought about this a second attempt or something, because your paper, three of you, Fang Xiao, Qimai, and you had this first attempt, and we thought probably it would be better to have second attempt. Then I changed my mind, because we think that will give people a hint that we will have a third one. Then there's sequential, and we know there's a countable number after the third, the fourth, and so on. So we decide just stop at here. Probably there will be a third attempt. I don't know. This was a joint work with my PhD student, Qing Wei. First question I need to answer is, why do we do this, right? If you look at these moderate deviations, we have plenty of literature for normal approximation. And then also we have this so rich literature on this discrete approximation. So we have very strong distances like total variation distance for unbounded functions, for Warsaw stand distance. We have many very good papers in this area. So I didn't think of writing a paper in this at all, because I believe it's just a learning process. We learn from these great guys. However, it really comes to my mind to do something on these tail probabilities. And so I started thinking I needed tail probabilities. And in statistical inference, then we talk about tail probabilities more often than the metrics. Actually, that was probably about 20 years ago. A statistician came to my talk. That was a statistical conference. And then after the talk, he approached me saying, you guys are doing useless stuff. I wasn't very impressed by this comment. But anyway, I was a very gentleman, and I didn't really argue that something was useful for what we are doing. Then, when I was looking at these tail probabilities, you will see that, in fact, probably what the guy said has some truth. We are doing useless stuff. I'm doing useless stuff, all right? Proving useless theorems. Why do I say this? Well, in the next bit, I will talk about this. Now, if we look at tail probabilities, why do we need tail probabilities? In statistical inference, I hope you still remember that in the inference, you have this null hypothesized statement, and then you look at the data you observe, and you propose a statistic, and then you put in there to see whether we have the values falling in here or in here. If we have values falling in either here or here, then we say, well, your null hypothesis is questionable, and the evidence is against your null hypothesis. And typically, these two tails adding up is something like 5% from Ronald Fisher saying if we make a mistake in one mistake in 20 trials, then it's regarded as something like acceptable. And then these tail probabilities actually determine the range of the rejection region. And so if the tail probabilities are not well calculated, then we don't really have much confidence of what we say. So this is the reason I started working on this problem. And here, what's this moderate deviation? I assume some of you don't really know what this moderate deviation is. And so this is a good example of this moderate deviation. Here we have independent and identically distributed random variables. And then we do some the sum and the standardize. We look at this tail probability of this, which one is this? This one is, right. We look at the tail probability compared with the tail probability of normal. And then you will see in this statement, essentially this is roughly 1. So namely that if you give this as 5% at the denominator, then the numerator is not far away from 5%. So this is very good. The issue here is, I started having problem is the C1 and the C2. We wanted to control this. We know this, when we have this capital O, we are very happy because we are doing theory. But if you do statistics, probably you will change your mind. And what's the range of the values we should apply this theorem? It's not really clear to me because I don't know the values of C1 and C2. So we also look at this number of real events. Here, we look at this pioneering work of Lewis in 1975. Already from there on, we have encyclopedia, this is Poisson approximation by Andrew and 2 others for this Poisson-related work in there. And so you can see here that the Poisson distribution with some modification, relatives, one way or another, you try to modify to make the Poisson, because we know Poisson has a mean and a variance, right? And so when your mean and the variance are equal, then you expand mean, then your variance also expand. So that will give us less flexibility. So somehow you can change the coordination of the mean and the variance to make Poisson fit the problem a lot better. Then we will have results of stronger metrics like total variation, which typically would not be the case for normal approximation. But for tail probabilities, you will ask, well, we don't need stronger metrics because we want to look at just the tail probability, which is bigger than or equal to. It's a kind of homograph distance. So can't we just use normal? Actually, I wasn't really convinced we should do a Poisson here because I believe once we talk about homograph distance, very often normal would be enough. Then I look at a concrete example here. We look at this IRD continuous random variables. We try to look at records. Look at records here. Then you will see X1 is always a record. No problem. It's always a record. So we ignore that one. Not interesting at all. Then we look at the next ones. So X2, if X2 is bigger than X1, it's a record. If it's less, then we don't have a record. So we look at this number of records in the sequence of IRD random variables. And Sn here is the number in this n IRD random variables. So this Sn actually is a boundary case where normality and Poisson can both be used. All right. Then if we look at approximations of this Sn, you will see the lambda n is the mean of Sn, which is just the sum of 1 over i's. And this sigma n squared is not far away from lambda n. Lambda n and the sigma n are very close. The biggest gap is about 0.65. 0.65. I try to do the calculation. You wouldn't get bigger than this. So in this case, you can see it's a perfect case. We look at whether Poisson works well and whether normal here works better or something. And if we look at this homograph distance, which is to be fair to normal and to Poisson, you will see normal approximation, the order is log to minus a half, and the Poisson here is log to minus 1. Both of them are very slow. All right. Nevertheless, theoretically, Poisson is doing better in this case. Okay, so how about tail probabilities? That really puzzles me. How about the tail probabilities? Well, typically in statistics, we look at 3 standard deviations away, or 2 standard deviations away. Normally, we would use 2 or 3 standard deviations away. And in my teaching, I never needed more than 3 standard deviations away in looking at the tail probabilities. So I pick up these 3 standard deviations away and compare these Poissons. We have 2 Poissons. One is based on lambda n, which is the mean of Sn, and one is the variance of Sn, and one is normal with the mean and the variance all fitting well to this. And so here is this comparison. And yes, I did the programming. I learned how to program, and I now understand doing research, you spend time, you may not make progress. But if you do programming, you do make progress every day. All right? So you have something every day to report. So in here, if you look at this ratio, all right, using normal to approximate Sn, and then you can see the ratio actually fluctuates somewhere between 4 and nearly 2. And there is no hope actually coming down to 1. That's what we are after. And so you say, oh, okay, this is not fair because normality, you look at normality. Normality here is not really accounting for all integers. It should be a 0.5 correction. So yes, I did. I thought about 0.5 correction, which actually we would do using, slightly pulling back a little bit. Look at the tail probability. You can see still not really doing better at all. So all these cases, you can see, are still far away from the target 1. And then we look at the Poisson. And if you look at the Poisson lambda n, which has a cell mean, that's actually going towards 1. Slowly, but happily, right? So that's something I was very encouraged. So then I thought, okay, how about I use the variance here to fit in? So you will see, actually, this is actually further away. So this tiny change of 0.6 something would change the ratio so much in this case. So that explains, in the case that actually David asked the question about these tests. And in fact, that's where the problem is. For normal, the tail actually is so thin, so small. And for Poisson, the tail is a lot fatter. So we somehow, if you are dealing with total varying distance or dealing with all these approximation metrics we are doing so far, we are looking at the middle chunk of this. However, if you look at this Neyman-Pearson lemma and you look at this chi-square tests, usually you would be just looking at the tail parts there. And so there are different methods. And so that actually reminds me the statistician saying that we are doing useless stuff, which is, to me, not polite enough. But it's there is some truth that we don't really care that much. We have a constant, done, right? To me, a constant is constant, but to them, it is not, right? That makes sense. So the winner of this, you can see, is clearly Poisson with lambda n. So there is no question about this for this particular case. All right, and then I move on to the next part, look at literature. So I started searching this, and I always believed that was for Poisson moderate deviation. It's more or less like normal. And actually, I also called Zhu Song to my office. I tried to learn some techniques in normal. And I believe I just need normal techniques, and with some twisting, I can get Poisson done. I don't need Poisson itself. And then you look at these articles, these are the 4 I can find, and probably I missed 1 or 2, I don't know. I'm very interested in this number 1 here, and then also very interested in this first attempt. There are 2 possibilities. The first possibility is they have something they are writing, and that means we shouldn't do anything, right? The second is they don't have anything. If they don't have anything, that's even worse, right? Because that means not really much contribution can be made to advance a lot in this one. So I now can see why this problem is actually a lot harder than it looks like. I thought it was easy, but it's not. So then I look at the tails of Poisson and normal. You look at these 2, and you will see there is acceleration of the tail probabilities against normality with 0.5 correction. Without 0.5 correction, then that's even worse. So this acceleration is very fast, you can see, to the 5th standard deviation away. And then if you look at further down, 1 standard deviation to 4 standard deviations away from the mean, you can see that this acceleration is reduced and tamed when this Poisson parameter is getting bigger and bigger. And so you can see here we face the problem that in the normality, it is very smooth, so you can move a little bit, but then for Poisson, it's not. It is, the tail is just very fat compared with normal. And then to 6 standard deviations away, you can see the acceleration here is a lot faster, that's 12,000. So you do the calculations, you will see actually, yes, these two problems are very different. So the conclusions are, I would like to summarize what we observed from here, not theoretical proofs, but just observations from our calculations. Poisson has a heavier tail than normal tail. And there is acceleration of the ratio of the tail probabilities beyond a few standard deviations away when lambda is not large enough. And unlike normal, looking at number of standard deviations away for Poisson is not going to work very well if the parameter is not big enough, especially something like this number of records. And small change of the value of lambda will give us a heart attack normally. So that's what the first observation we can see. Let's look at the second observation. We'll look at the mean and the variance. We know Poisson has one parameter which plays two rules. One is the mean and one is the variance. Which of these matters here? So let's see here our concrete calculation. And we'll look at the binomial first. Well, if we can't do well in binomial, then certainly we should adjust our tools. So here, Poisson are fit with the same mean. And typically, we look at this tail probability of this binomial against Poisson. And then this is same K, which has been used by the moderate deviations in normal and as well as in Poisson. So we compare these two. You can see when n becomes large, actually there is a gap. And this gap here is systematically away from 1, which we are after. So there is no such a thing of converging to 1 at all. So no wonder that we can't really do well when we are dealing with this moderate deviation ratios. So we look at possibility of correcting this error, this bias. We try to correct this one. And then you can see here, Wn, I try to do the same thing, but then I correct this one by looking at how many standard deviations away. So this is standard deviation of the Poisson. This is standard deviation of this Wn. This is the mean of Wn. That's the mean of the Poisson. And so they are fair comparison. So they should be close to 1. All right? Or equivalently, you can do the other way, but you can't mix them up. So it doesn't really matter how you do this. You have to somehow to be a fair comparison. Then you will get the right bound. So the conclusion here says is the variance of the Poisson matters in this case because it tells me how many standard deviations away. And then if we adjust this center of the Poisson a bit, which is called translated Poisson or shifted Poisson, it doesn't really matter what you call, and that will give us trying to get rid of this systematic bias involved in this case. So then I do more calculation. You can see, actually this is a very, well, we believe standard deviation, yes, the standard deviation of this is around the square root of n. So multiply the error by square root of n should give me some idea how this would behave. And if you look at in here, there are a lot of fluctuations, but then this is a big range of the numbers. So we should zoom in to see what really happened. That's what happened in here. So how could this happen? We have sometimes dropping down, right? Sometimes dropping down. Well, that's actually because if you look at the ratio in here, the ratio here are not synchronized. They are not synchronized. And so if you look at Poisson and some rounding error to the next one, you will drop the probability by a lot. And it's not normal. In normal, you standardize normal, that will be the same thing. There are no two normals, right? And the Poisson is abnormal. All right, so you cannot somehow to compare one Poisson with another Poisson. And so this unsynchronized part would give me this shocking part of this observation. That raises the issue that in the Poisson moderate deviation, the task is very hard how to adjust the parameters. Then we look at further by changing this p into 0.01. And then there is a periodic behavior purely because of this 0.01, which gives us this rounding. One of these moved to the next integer, the other one was staying in the integer beforehand. And so they can't really move together at the same time. And zoom in, you can see the same phenomenon happens to all the cases. So then let's look at a result by Lewis and Fang Xiao and Qi Man. That's in 2013. And we try to understand what they did in this paper. And so here, to introduce the result, I just use this size bias distribution. In the morning, Larry talked about size bias distribution. And here, I assume that some of you don't know what this size bias distribution is. So here, that is lambda is the mean of W, and then this distribution, the WS is said to have the size bias distribution of the W in here. And the size bias distribution obviously was introduced earlier than palm distribution, although one is for the process and the other is for random variables. They are doing the same thing. That is, if I know the information happening of W, then I would change my perception about the distribution of W. So in this size bias distribution, the three guys prove this total variation distance. And then also, they assume in here that if this size biased random variable WS and W are defined on the same probability space in such a clever way that the gap in here, when that's a Poisson, this will be just equal to 0. Just to remind you, the size bias distribution of Poisson is Poisson plus 1, meaning I know somebody has happened at that spot, and then the extra bit is Poisson. And so they ask for the delta here to take values from -1, 0, and 1, which to me, for special cases we can do, but in general, this is a condition very hard to verify. It's really something to me, I just couldn't really construct the random variables together in such a manner. Then you look at this condition here, is to look at the conditional probability is bounded by delta 1, and this one bounded by the delta 2W. And then we have this ratio, which is essentially bounded by a constant, which actually is the right thing because you can't do better. Just this number of records tells us you can't really do better than just a constant in this case. Then here is a toy example, and I can explain what this size bias distribution is about. This size bias distribution is calculated in the following way. We have the sum of independent below-linear variables, and then you can do some calculation by splitting the W into these individual xi's. And then we can do the conditioning xi equals 1 with this probability pi. And then divided by rho, divided by mu here is to adjust this one into a distribution. The pi minus mu will form a distribution. And that one, then we have this wi plus 1. So then we can rewrite this one into this I, and this I is just constructing this size bias distribution. So we have this I taking values from 1 to n valued random variable independent of xi's, and then the ws can be written in the wi plus 1. What we do here is I chose an index according to the distribution in here, and then I then replace that value xi by 1, and the rest of them as they are. So this is for this size sparse distribution. Then for this case, we can easily verify that this one here is delta here is this xi, and so we don't really have anything for the first parameter. And then the second one, you can do some calculation, and then you take the maximum out. And then we are left with this. And this guy here, we know what to do because the sum is the map, that's W. That will give me this relationship in here, which means we know what this delta 2 is. The delta 2 is the maximum divided by mu. And then we plug in here, we will have this bound. This essentially relies on the maximum of Pi. And if we look at in this number of records, then this will not be small. This will stay here. It's a half. So that will be a half. And then again, this is a constant. And what is C? We don't know. And C here typically is large. And so we don't really know how large the C is. In general, it's hard for us to see this constant C. It's unspecified. Then we have this matching, which is very similar. The matching is you fix this I, then you random permute these integers 1 to I, and then you look at how many of them are not shifted by this random permutation. And this, then the total number of them is our W in here. We try to look at what is size sparse distribution of the W, and I decide to write a bit in here because for those people who are not familiar with the size sparse distribution, and I think this is a good exercise how you can do this, you know. What you do is you start from here. W, splitting, xi, look at this distribution. That's your wi, and giving me this. 1 over n is a distribution, and then we should construct from here. That's this idea, to construct the size sparse distribution. And then we know that the variance of this case is 1. The mean of this is also equal to 1. In this case, we don't have the variance becoming large, and so we don't have the luxury in the number of records case. So here I decided to draw a picture for you how to construct this size sparse distribution introduced by Chatterjee and Diaconis and Vekis in 2005. Essentially, we use the original pi. What we do is randomly pick up a location which is equally likely I here. Then if I see in here, I check, well, does my pi here shift I away from the original location? If it doesn't, okay, then the pi s, the size sparse distribution, stays the same as pi. If it does, then we look at in here. If it does, then no worries. Where did you shift I? Okay, y is shifted to here. So we say, go back to where you are from. Right? Sounds very familiar. So this one then goes to there. Okay? And then I know the position because I was shifted away to here. Right? And so there must be somebody else was shifted to my I here. And then I say, go, not to stay here, move to here. Then that's pi s, done. So that's the original idea of this construction. And you can write into this mathematical formula, and this is just a formulated idea into a mathematical form. And then with this coupling, the three authors prove this, this bounding here. Especially if k is fixed, then you can see the order of this is 1 over n, which is a very good order in this case, actually. And so, as I said before, we can either look at the mean or look at the variance of the Poisson, and we try to do some adjustment. And in fact, we will do both here, giving us flexibility that if necessary, we can shift the Poisson a little bit. So here, again, we start with Poisson, we start with W with a non-negative integer valued random variable, and the mean is mu, and the variance is sigma squared. And then we leave A here. A is a constant, which you can twist around. And then we look at difference between mu and I, and that will be the fitted Poisson. So that will give us the flexibility of moving the location as well as changing the variance of the approximating Poisson distribution. So then we can prove the following result here. And the reason we ask for this in here is because one standard deviation away is minimal requirement when we look at these moderate deviations. We look at the tail probabilities. Typically, we need 2 standard deviations away or even 3 standard deviations away. So we ask for x here bigger than or equal to 1 to make this useful for our statistical inference purposes. So here, you can see we have the bound here. And this bound here is very specific in here. We don't have any unspecified constants. And so you choose the parameters, you plug in, you can see this, if W is Poisson, then this will be just 0. And if we choose mu equals lambda, this is 0 again. And then, this one will be just 0 as well. So you can see here, this is a good, in my view, is already a very good result. So when A equals 0, that's comparable to what the paper, what the results in the paper by Lewis and Fanshaw and Qiman. So if you look at their result, they have a C in here and this one here. And here we have this e to x squared plus 1. And I got very encouraged when I saw Gaziner's talk. Because if you put x equals 1, that will be e to this one squared. That's about 8, right? And then times 3, that's 24. A lot better than the bigger constant. So I thought, well, not too bad in this case. And if x equals 2, it's still not very big. So I'm quite happy to see this result in here. And so in here, these constants usually are relatively hard to obtain. And you look at the constants, but they have to be in the calculation of the difference of the two. And here, we can see a difference straight away coming into this upper bound. We don't need to introduce this delta 1 and the delta 2. So our bound here is easier to compute and also no unknown constants. And so that looks a lot nicer. And so, of course, when we do something, we try to do better. We always try to improve on what we do. And here we have, we use this local dependence structure. This structure was introduced in the paper by by Lewis and Qiman in the paper of 2004. We look at this LD2, and I even didn't try to change the number to make sure those people look at our dependence and they are familiar with dependence structure, then they don't have to check what this is. Anyway, for those people who probably are not familiar with this, we are looking at the dependence structure in the following way. That is, we never use this color. So this one here is, you draw this I, and we look at the dependence layer of AI. That is, the random variable here is independent of outside, and then the random variables inside here will be independent of even further away. So that's the two layers of dependence, and so we call this LD2. And then in this case, again, we look at this W is the sum of these locally dependent random variables, and the mu is the mean, and sigma squared is the variance. And then we look at this one here, essential supplement here. This is just purely to simplify our upper bound. And so this one here is roughly equal to the maximum probability, because the maximum probability determines how fast the speed is. And so in here, we can see the bound here looks in the following way. This is roughly 1 over standard deviation. This one, roughly 1 over standard deviation. And this one is, we look at this local dependent structure around here. This number of random variables is, we sum them up to get the I. And then the number of random variables in here are added together to get this part in here. And so this part, if we do calculation, typically that will cancel with lambda in here. So this constant will stay. And this one is 1 over square root of, 1 over the square root of variance. All right, this theta I. And then this one here, if your lambda and sigma squared are close, this will be relatively small because lambda will increase. And this one will be very small because of this turn-off inequality or something you try to apply in the particular cases. You can find this is relatively small. So now, we can say here, do we need moment generating function? Because you can see in the moderate deviations for normal approximation, we need this moment generating function to look after the right tail. So the right tail should not be too fat. If the right tail is too fat, then we come back to the problem. Normal tail is too thin, and so we compare a fat tail with a thin tail, so there's no hope we have the ratio converging to 1. And so, do we need that one here? But actually, I worked on all the examples I could see. They do satisfy the moment generating function requirement. That is, I said the tail should not be too fat. However, in our case in here, I can't see why this right tail is so important. I really can't see because Poisson, the tail is already very fat. So you have a fat tail against another fat tail, who cares? Right? They are both fat anyway, so they should be offsetting very well. So then they say, well, this is Stein's workshop. You talk about this. Is Stein's method used? Well, I not only mention Stein, also mention the academic child of Charles Stein. That is the Stein-Chen method, all right? So that's Louis, right? Academic child of Charles Stein. And so we can look at in here. This is the tail probability we are looking at. And then this is a very heavy slide. Try to explain what we are doing. So we look at this Stein's equation. We try to solve for this f. Look at the property of f. So then we managed to use this coupling and Markov chain y of this solution. And then you can see in here that this solution would satisfy the delta f will look like in this way. So in this way here. So this is k minus 1. And then all of a sudden, that will jump to in here. And then this is for delta f, that behaving in that way. So once we have this, then it's actually very, very easy for us to extract these bounds and using some relatively crude estimates. Still very crude in here, and we can't really do beta at this moment. So this here, the first part is bounded by this, and this Poisson is already in here. This is tail probability of Poisson. X. Oh, this X is correct. This. K minus lambda. Yeah. So how many standard deviations away from that? So that's X. So we have this is a constant. All right. Do you know this how many standard deviations away? Then you know what this is. And so if you look at this, we have the bound, which is 1 over lambda, which is already very nice, and including the tail probability. That's where the difficulty is. We get this tail probability, and we also had the right side of this. We divide it into two parts. This is the part in here to the left. That's the other part to the right. And then both are controlled in much the same manner. And so we have the delta F is no worse than the two of them. And then the other two will be just this gap in here, just this gap. So the coupling would enable us to see this in a clear picture to get this property of the Stein's factors. So we look at examples, right? Just putting back into the cases we have studied before. So the xi would be Poisson binomial distribution, and we'll put them back in. And then lambda is the difference, and then the variance is sigma squared. We look at the Poisson, we look at the relationship, something of this kind, something. And actually, I try to, simplify what I'm saying. And so if lambda is close to sigma squared, this would be getting smaller, all right, when you have the mean getting bigger. And this one here is also relatively small. And so indeed, we can see the difference will become small after this adjustment that will converge to zero. Then we look at matching problem. We get this bound again. If x is equal to 1, which x is k minus 1 in here, because the standard deviation is 1, lambda here is 1. And so that will give us 48, roughly 48 is the constant, divided by n. So that's very encouraging for this case. And for 2 rounds, typically I wouldn't report the results in this way because I don't want to bore the audience with all the details. But then just focus on this n under this is denominator, And so this is the valuable part, denominator. And so all of the others, they are constants. And so you can see this actually converges to 0 when n becomes large. And so the take-home messages I would like to say in here, because if I introduce this coupling, that would require some heavy techniques involved in. The ideas are very simple. And so take-home messages here are for the counts of rare events, all right? The tail probabilities actually can be done better by Poisson because Poisson is more suitable for this kind of fat tail distribution. And the robustness of the tail behavior of Poisson for large n has not been considered in this upper bound. So there must be something to do with lambda. When lambda is getting bigger, all right, it's getting a little bit more tamed. And so the behavior should be better in this case. But I can't see. My bound here does not depend on the lambda to be very big. It does not. So it must be, the constant must be improving. So I don't know what to do this. The next is, I believe the bound should be, a third of this. So then, we don't know much about lower bound. Thank you very much for your time. Thank you. Yes. Yeah. I think so. Our bound here is so nice. Well, I'm saying something, of course, right? I would say it's nice. If I don't have any confidence, then people wouldn't have confidence. All right. Yes, I think so. As long as you can construct this, somehow you have some local structure there, then you can. Yeah, well, you need to be careful with this dependence of the range. If the range getting too big, then we will be in trouble again. This log issue, will probably come in. Yeah. That one, ask Andrew. That's in his book, in the appendix, where he came up with all these estimates of Poisson tails. And then who couldn't find a way to get it beta. All right, I don't like it. But then I'm encouraged because numbers here are not really very big. Now, it's actually accelerating, which coordinates with my observation. When your standard deviation is away to 6, that shoe going out very, very fast. Yeah, numerical calculation tells us this is probably something we cannot improve that much. Yeah. 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 Mm. Mm-hmm. Mm. Yeah. Yeah. Mm. Yeah. 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 All right. Thank you. Oh, that's because of unsynchronized K, because I'm using one K against another different K to somehow look at how many standard deviations away. So this is unsynchronized, so they will jump at different times. That is, if we, well, I should go back and then you will see. They are actually, usually I wouldn't do this kind of thing. I know students would be annoyed for me doing things. Right. If you look at it here. So here, that was NP. And this one is sigma n squared. So there's a difference between the two. So this one, when this one moves from one integer to the next, for the Poisson, it may not be moving. Are you with me? Yeah, and because when n increases, it may not be moving in the synchronized manner. So one of them moved, the other one doesn't move. In normal, you don't have the problem because it's changing continuously. But for Poisson, it's not, right? You change from, say, 0.99 to 1.01. You suddenly lose 1 here. And the Poisson, that will be a heavy loss for the Poisson tail. And for normal, moving this little bit, very tiny change. So that's the difference. And this difference will be just in our ratio here, because it changes so much in terms of the ratio. So the Poisson actually is a lot harder than normal because of this. And then you say, well, why don't you just let them synchronize? Well, that's a different matter. Once you synchronize the two, then they don't converge to 0 at all. You don't. All right, so you don't have this. So you can't win. There's no win-win situation in the case. Yeah, I can't think of a way you can win-win. No, we can't. Thank you.
Time again.